Light has absolutely no mass, but it carries momentum. When it strikes an object, it exerts a physical push. We can see this clearly on a cosmic scale. The tail of a comet points away from the sun because the radiation pressure of sunlight physically sweeps the dust particles backward. Physicists understood this behavior in a vacuum perfectly well. The confusion began the moment that same light entered a denser, slower medium, like a pool of water. By the early 20th century, physics was split between two mathematical models. Both equations attempted to describe what happens to light's momentum inside matter, but they predicted exact opposite realities. The math collided directly with the real world. Without knowing which equation was correct, scientists realized they lacked a working mechanical model for how light actually interacts with matter. On one side was Hermann Minkowski. In 1908, he proposed a theory arguing that when light enters a dense medium, its momentum actually increases. A year later, Max Abraham published a rival theory. He argued the exact opposite, that light entering a dense medium loses momentum. This illustrates Minkowski's consequence. If light gains momentum entering a liquid, the liquid reacts in the opposite direction, physically pulling the surface outward. Abraham's math demanded the opposite. If light loses momentum, it pushes the surface sharply inward. The problem lingered for over 60 years. The push of light is microscopic, and nobody had the technology to build an experiment sensitive enough to isolate such a tiny force. Resolving this paradox became an obsession. The surface either goes up or it goes down. Only one of these physical reactions could actually happen. In 1972, a researcher at Bell Labs named Arthur Ashkin set out to solve the physical problem.
He built an experiment to fire a highly focused, extremely powerful pulsed green laser straight down into a microscopic point on a dish of water. The main obstacle was heat. A high-powered laser usually boils the water it touches. If the water boils, it moves, masking the microscopic mechanical push of the light itself. Ashkin solved this by restricting the laser to 60 nanosecond pulses. He chose green light specifically because water barely absorbs it, effectively eliminating thermal lensing. By removing heat from the equation, the surface of the water became a perfectly isolated arena. Any movement they captured would be pure mechanical force. The laser fired, delivering a peak power of 4 kilowatts, directly into a spot just over 4 micrometers wide. As this schematic shows, the water surface lifted upward. It bulged into a distinct microscopic convex lens that scattered the light. Ashkin ran a secondary test. He fired the laser from underneath the water up toward the air. The boundary still bulged strictly outward. The data was unambiguous. As Ashkin wrote in his 1973 paper, the outward net force perfectly agreed with the predictions of Minkowski. The physical evidence appeared definitive. The experiment proved Minkowski's equation correctly predicted reality. But the final paragraphs of Ashkin's paper contained a caveat. The results didn't actually disprove Abraham's theory. Prompted by the strange mechanics of the water lens, physicist J.P. Gordon conducted a new theoretical analysis of the problem. Gordon introduced the concept of pseudomomentum. The interaction between light and matter splits into two distinct domains. Minkowski's equation strictly describes the mechanical boundary force. This force predicts the macroscopic drag pulling the water's surface upward, precisely matching what Ashkin photographed. However, that surface reaction only accounts for the boundary. It leaves the actual internal transport of energy unexplained. Gordon concluded that Abraham's equation remained completely valid. It describes true kinetic momentum, the way electromagnetic energy actually travels through the space inside the water. These equations describe two halves of a single reality occurring at the exact same time. Ashkin's visual experiment was the vital catalyst. It provided the exact mechanical evidence needed to force physicists to reconcile the two models. The 60-year duel ended without a single victor. The physical universe requires both mathematical perspectives to accurately describe the nature of light.